Okay, propositional theorem proving. A more efficient method of determining entailment than model checking is the theorem proving method. And this basically involves applying rules of inference directly on the sentences in the knowledge base to construct a proof without consulting models. Now, in order to explain this method, we need a few more terminologies. 1. Equivalent. Two sentences, alpha and beta, are said to be logically equivalent if they are true in the same set of models. And in that case, we write alpha is equivalent to beta. Example, obviously because AND operation is commutative, P and Q and P are logically equivalent. So this is one term. Next is, when do we say a sentence is valid? A sentence is valid, sometimes it is called a tautology, if it is true in all models. Any possible model you can think of, that sentence is valid in it. So it becomes a tautology, or it is simply said to be valid. Example, A or not A is definitely always true, because any sentence is either true or false. So if you or A and not A, definitely you're going to get true. Similarly, A implies A is always true, and A and A implies B, okay, will imply B. So again, these are all examples of valid statements, but they are really obviously true. That's why they are called a tautology. Now, validity is connected to inference via deduction theorem. We're going to see later on that it's easy to prove something is true if we can show that it is valid. So it helps us to do theorem deduction basically. So for example, KV entails alpha if and only if KB and alpha is valid. Yeah, so in trying to prove this, we only need to prove this, that KB and alpha is valid. If we can prove that, we don't have to prove this one. It's automatically implied. Next term is satisfiable. So a sentence is satisfiable if it is true in some models. For example, A or B will be true in some model, and therefore it is satisfiable. A sentence is unsatisfiable if it is false in all models. For example, A and not A will be unsatisfiable. A and not A, if you AND them, you're going to get an empty set. Okay, so it is not satisfiable. It is not true for A to be true and to be not true at the same time. You will get false. Okay, so this idea allow us actually to do proof by contradiction. Says satisfiability is connected to inference via the following. KB entails alpha if and only if KB and not alpha is unsatisfiable. So if we cannot satisfy KB and alpha, it will allow us to reach a contradiction. Okay, because as we said here, if KB implies alpha, then the statement KB and alpha is satisfiable. The last statement here is saying there is no model for which KB is true and alpha is false. This is basically what is the meaning of this. And therefore we can conclude that KB entails alpha. if we can prove this contradiction, then it automatically prove KB entails alpha. Right, so with this, we can now try to attempt the propositional theorem proving methods. The first one is using inference rules. So in theorem proving, the following pairs of sentences are equivalent, and one can be replaced by the other. So I have a whole list of them. I think most of them are obvious. The first one is saying and is commutative. Alpha and beta is the same as beta and alpha. Also, or is commutative. Alpha or beta is the same as beta or alpha. And then there is associativity of and. So alpha and beta, all and gamma is the same as alpha and beta and gamma. Okay, and similarly there is associativity in O. And then there is a double negation elimination. Not alpha is equivalent to alpha, so we can eliminate the not. If you double negate any sentence, you're going to get the same sentence back. Okay, and then there is contraposition. If alpha implies beta, then it follows that not beta implies not alpha. Okay, if you change the sign, then you can swap the beta to become the first one, to become the premise, and the not alpha to become the consequence. Okay, so these two statements or sentences are equivalent. There's also what is called implication elimination. Alpha implies beta is equivalent to not alpha or beta. You can also eliminate bidirectional, so it's called bidirectional elimination. Alpha if and only if beta is equivalent to alpha implies beta and beta implies alpha. Okay, so usually the steps to follow to remove the bidirectional: first, convert it to only imply, and then use the other equivalency to even remove the imply. We shall see that in a moment. The next two equivalencies are based on De Morgan's theorem. So it's saying not alpha and beta is the same as not alpha or not beta. Alright, so basically if you push the not inside, just swap the and with or. Alright, this is first De Morgan's theorem. The second one is about is similar but with or. So not alpha or beta is equivalent to not alpha and not beta. So these two De Morgan's theorem are also very useful in this inference rules method, as we shall see. And the last two are about distribution. First, distribution of and over or, and then distribution of O over and. So here we have alpha and beta or gamma. So we're going to distribute the and. So we're going to have alpha and beta or alpha and gamma. Okay, and the other one is the opposite. We're going to distribute over the O. So alpha or beta and gamma is equivalent to alpha or beta and alpha or gamma. Yeah, so this we're going to find them very useful, but there are two more, not exactly equivalent, but they are going to be useful. So in addition to the equivalent sentences, each of the following premises, the top part, can be replaced by the corresponding conclusion, which is the bottom part. Okay, so the first one is called modus ponens. Modus ponens. It says if alpha implies beta and alpha is true, then we can conclude beta. Okay, this seems obvious. Alpha implies beta and alpha is true. So definitely the two will, the consequence or the conclusion will be beta. So basically the result depends now only on beta. If beta is true, we will have true. If beta is false, we're going to have false. Yeah. Okay, the second one is called AND elimination. And this is how it goes. It says if you have alpha and beta, then it can reduce to just alpha. Okay, it's like the example I was giving you earlier. Ali and Omar passed the exam. So obviously, Ali passed the exam. Yeah, so we can, and this can also be beta. So alpha and beta can be just beta. Basically, this premise will give rise to the one below, which is called the conclusion. So it can help us to conclude that alpha is true. Now notice that in this case, the opposite is not necessarily the case, and you cannot have beta at the top and these two at the bottom. Whereas for the equivalences, we can swap them. Say all equivalent sentences can be represented in the form of premise and conclusion. For example, the bidirectional alpha, if and only if beta, we said is equivalent to this, so we can say this as the premise will give this as the conclusion. But we can also do the reverse. If we have this, we can have alpha if and only if beta as the conclusion. Okay, now but this is only possible for the equivalences that we saw in the last slide. You cannot do the same with these two additional ones. Okay, I hope that is clear. So we're going to find this premise and conclusion pairs very useful when trying to generate inference using rules. Example. Now let us apply our inference rules and equivalences to the Wumpus world. So going back to the Wumpus world to make sure what we have just explained is clear. So we start with a knowledge base containing our sentences R1 to R5, which we discussed before. Okay, I repeated them here just for easy reference. So based on this, we want to prove that not P12 is true, meaning there is no pit in cell 12, just by applying the rules, not using model checking this time, just to show you how this method works. So first we apply bidirectional elimination on R2. So let's start with R2. R2 says there will be breeze in 1-1 if and only if there is a pit in 1-2 or there is a pit in 2-1, if there are pits in the adjacent squares. So that we can use bidirectional elimination to change it into this. Okay, basically it becomes B11 implies the other one, P12 or P21, and the reverse, P12 or P21 implies B11. So this we obtain by simply using the bidirectional elimination. Next, we apply AND elimination on R6. Okay, let's try that. We're gonna eliminate the AND. Well, AND elimination, if you remember, it says if you have two sentences, alpha and beta, as your premise, you can just choose one of them, either alpha or beta. So this time we choose this one, P12 or P21 implies B11. Okay, if Ali and Omar both pass the exams, it also means that Omar passed the exam. Alright, so this is called AND elimination. Next, logical equivalence for contrapositives will give you the following. Alright, so if this implies that, then it follows that not B11 will imply not the other one. So not P12 or P21. This is just by applying contrapositive equivalence. Now apply modus ponens on this R8 and the percept R4. Okay, R4 says there is no breeze in 1-1. So if there is no breeze in 1-1, meaning this is true, what can you conclude? It means this is also true. If this implies that, and this is true, then by modus ponens, what we have is just this, the result of this. So now we have R9, which is not P12 or P21. Let us apply De Morgan's rule and see what we're going to have. Okay, so applying the De Morgan's rule, you remember De Morgan says if you have not and you pass it across, then you just have to change the symbol here. If it is AND, it becomes OR. If it is OR, it becomes AND. Okay, so we have R10, which is not P12 and not P2. And what does that mean? It means there is no Pete in 1-2, and also there is no Pete in 2-1. This is the conclusion we're able to reach. Neither cell 1-2 nor cell 2-1 contains a Pete. This is what this sequence is able to prove to us. And therefore our original alpha, which says cell 1-2 does not contain a Pete, is actually true. Okay. Next is inference as a search problem. We found the proof of the last example manually by repeated application of the rules. However, we can apply any of the searching algorithms that we learned in the previous lectures to actually come up with the same conclusion. We just need to formulate the problem as a search problem. And we can do this as follows. Initial state will be our KB. What do we know so far? So our knowledge base will form our initial state. Actions. What are going to be the actions? So the set of actions are simply going to be the rules that we can apply. Okay, the set of actions consists of all the inference rules applied to all sentences that match the top half of the inference rule. So if we consider those rules as in the form of premise and conclusion, so our action will consist of applying the sentences that match the top part, which is the premise, and the result of the action will be the conclusion part. Okay, so those will be our actions. So the results the result of an action is basically to add the resulting conclusion to the KB. So each action will allow us to add one more sentence to the knowledge base, because based on the premise we're going to get a conclusion. Just add the conclusion to the knowledge base and continue doing that until you reach the goal. Now, what is the goal? The goal is a state that contains the sentence we are trying to prove. Remember, we are trying to prove that alpha is true. So all you have to do is keep applying the rules using any of the searching algorithms. You will be obtaining another sentence from applying the rule. Add that conclusion to your KB and keep doing that. Eventually you will find the searching algorithm will actually find the answer for you. All right, so that's what we are saying here. Therefore, searching for proofs can be considered as an alternative to model checking. In fact, it is more efficient than the model checking because it's going to ignore all irrelevant sentences. Remember, the model checking will look for all possible scenarios. Whether they are relevant to the query or not, they're going to be checked. But the searching approach it will actually ignore those symbols that are irrelevant. For example, if you look in the last slide where we did it manually, there was no place where we use B21, P11, P22, and P31. If you check the last slide, there is no occurrence of any of those here. And therefore, it means we are not looking at all possible symbols. Only symbols that relate to the problem we are trying to solve, applying the available rules. Okay? And therefore, the searching method is not going to be as expensive as the model checking, because model checking has to check for all possibilities. Okay, so this is basically what the searching approach involves. The last approach we're going to look at is called proof by resolution. Which is even more powerful than the searching. So it says inference rules discussed so far are sound. They are good. Okay, sound, remember, means if they generate a sentence, that sentence is always entailed by our KB. But what about completeness? Are we sure just following the rules we will eventually reach the target of answering the query? Yeah, so such algorithms such as iterative definite search that we saw before, they are complete. But if the available inference rules are inadequate, then obviously the goal will not be reachable. Okay, so the problem is not with the search, but the actions that you are applying are not complete, because none of them will lead you to the actual goal. And therefore, there may be a situation where the algorithm will not be complete. You will not be able to prove what you are trying to prove. Not because of the searching algorithm, but because you have inadequate rules. So this is the problem. Now we're going to introduce another approach, which is proof by resolution, and it involves just one rule called resolution, that gives a complete and sound inference algorithm when you couple it with any complete searching algorithm. Okay, so if you apply searching algorithm to this resolution rule, provided your searching algorithm is complete, definitely you will arrive at an answer. So it's going to be complete and sound as well. We begin by using a simple version of the resolution rule, again as you will expect, applied to our Wumpus world. So consider the state where the agent returns from 2-1. So the agent went 2-1 and couldn't make a conclusion because there was a breeze, but it couldn't decide whether the pit was in 3-1 or it was in 2-2. So let's assume it came back to 1-1 and then goes up to 1-2. Okay, so in 1-2 it perceives a stench but no breeze. So we're going to consider this new information and add it to our knowledge base. If you recall, so far we have generated 10 sentences, assuming those 10 sentences are in our knowledge base. We're going to add the new information that we just obtained. And number one is that there is no breeze in 1-2. See, when it comes to 1-2, what it perceives is stench, no breeze. So we can add that as R11 to our KB. Okay, the second thing we can add is that there will be breeze in 1-2 if and only if the adjacent squares contains a pit. So what are the adjacent squares to 1-2? They are basically 1-1, 2-2, and 1-3. Okay, so based on this, therefore, we can say B12 is true if and only if P11 is true, or P22 is true, or P13 is true. It says here, by the same process that led us to R10 earlier, we can now derive the absence of pits in 2-2 and 1-3. Okay, I remember, of course, already we said there was no pit in 1-1. So we say here, sentence number 13, 2-2 does not contain a pit, and also no pit in 1-3. No pit in 1-3. We can also apply biconditional elimination to R3, followed by modus ponens with R5 to obtain the fact that there is a pit in either 1-1, 2-2, or 3-1. Okay, so either P11 contain a pit, or P22 contain a pit, or P31 contain a pit. And now comes the first application of the resolution rule. The literal not P22 in R13 resolves with P22 in R15 because they are complementing each other. Okay, so if they are complementing each other, basically what we do is we eliminate them. This is what is called resolved. So they resolve themselves. Okay, so this is actually the idea of this method. Anytime you have two complementary sentences, they automatically resolve themselves. All right, and therefore what we are left with in this R15, we will eliminate P22. So we are left with just P11 or P31. So what is the meaning of this? It simply says if there is a pit in one of 1-1, 2-2, and 3-1, and it is not in 2-2, because we have confirmed it is not in 2-2, then it is either in 1-1 or 3-1. This is the idea. Either it is in 1-1 or 3-1. Now similarly, the literal not P11 in R1 will resolve with the literal P11 in R16 to give us now a single sentence. R17 is just P31. In English, what it means is if there is a P in 11 or 31 and it is not in 11, then definitely it is in 31. So this is how we concluded where the pit is. The pit is actually in 3-1. Now the last two inference steps are examples of a unit resolution inference rule. So what does unit resolution inference rule says? So if you have something like this where L is literal, so it's a single symbol, and Li, so there is one particular Li here that is complementary with M. So Li and M are complementary, meaning one is the negation of the other. Then instead of having all of them, we are actually going to eliminate both the M and the Li, so that what we are left with is L1 until Li minus 1, and then skip the Li, start from Li plus 1 until the last one, which is Lk. Alright, so basically what it says is if you have a single literal which there is a complement of it in a sequence of O's, then you can actually eliminate both. Okay, this is what is called unit resolution. Unit in the sense that it is single. Okay. So thus the unit resolution takes a clause which is a disjunction. It's a combination of O's, L1 or L2 or L3 or L, not and, it's O. Okay, so that's what is called disjunction. So it takes a clause which is a disjunction of literals and a single literal and produce a new clause. So that new clause will eliminate the one that has the complement. Okay, so note that a single literal can be viewed as a disjunction of one literal, also known as a unit clause. Yeah, so this one literal can be considered also as a clause, because it's not just one element. This is actually where the name unit is coming from. It consists of just one literal. Now the unit resolution rule can be generalized to the full resolution rule. Okay, the full resolution rule, the difference here is the second one here is not a unit. It's actually another clause. So we have two clauses, one L1 to and L1 or L2 and so on until Lk, and the other one M1 or M2 and so on until Mn. And then we have one of the literals here to be complementing one of the literal here. In that case, we're going to obtain another sequence in which those two complementary literals are eliminated or they are resolved. So only going to have L1 until Li minus 1, skipping the Li, and then Li plus 1 until Lk, or the rest here excluding the Mj. Okay, so until Mj minus 1, skip the Mj and start from Mj plus 1 and so on until Mn. Okay, this is basically what the resolution rule is about. Of course, where Li and Mj are complementary literals. This is the only condition for you to be able to eliminate them. So this says that resolution takes two clauses and produce a new clause containing all the literals of the two original clauses except the two complementary literals. Let's take an example to make it more concrete. So suppose I have P11 or P31 as one clause, and another clause, not P11 or not P22. So these two, if we apply the resolution rule, will give us P31 or not P22. Why? Because P11 and not P11 will resolve themselves. So we are left with just P31 or not P22. This is the idea of the resolution rule. One more technical aspect of the resolution rule is that the resulting clause should not contain repeated literals. In other words, should contain only one copy of each literal. What does that mean? We need to remove multiple copies of literals, and that is called factoring. So for example, if you have A or B, and also you have A or not B, then clearly B and not B are complementary, so we're going to eliminate them. So we'll be left with A or A. But we don't repeat a literal. So actually what it means is we're going to have just the A. This is the idea of proof by resolution. Now the resolution rules applies only to clauses, of course. Okay, that is disjunctions of literals. So does that mean it applies only to KBs and queries that consist of clauses? This is the answer. The answer is actually every sentence of propositional logic is logically equivalent to a conjunction of clauses. So we can convert any sentence to conjunction of clauses, and therefore we can apply the resolution rule. A sentence expressed as a conjunction of clauses is said to be in conjunctive normal form, or CNF. Alright, so we're going to show next a procedure for converting a KB, for example, to CNF. We illustrate the procedure by converting the sentence B11 if and only if P12 or P21. We want to convert this into conjunctive normal form, CNF. Okay, we do that in this slide. I repeat the expression here for us to see what is happening. First, we eliminate the biconditional, following the rule for eliminating biconditional. If you recall, alpha if and only if beta can be replaced as alpha implies beta and beta implies alpha. So with that, what we have, we will replace this with imply. So B11 imply the other one, and the other one implies B11 as well. Next step is to eliminate the imply itself as well. We remember that there's a rule that says alpha implies beta is equivalent to not alpha or beta. So therefore, if we apply that, we can replace this by saying not beta or this one, P12 or P21. And similarly, this one, we can replace it by saying not P12 or P21 or B11. And the next step is CNF requires not to appear only in literals. Yani you cannot have not here outside bracket. It has to be on a literal. So we can move it inward using our one of the De Morgan's theorem. Okay, the one for the O in this case. Alright, so if you have not alpha or beta, O is equivalent to not alpha and beta. Just convert the O to AND. So with that, this is what you have. This is the same as before, not B11 or P12 or P21, and not P12 and not P21 or B11. The last step is to do a distribution on this O, because we want to eliminate this AND. Remember, for a clause, all the terms must be in terms of O's. So AND of O's, this is what we want. So if you distribute these O's, okay, that's what it's saying here, step 4. Now we have a sentence containing nested AND and O. We applied the distributivity law, and if we do that, this is what we have. So no change in this first term, but here we apply this or B1 across the bracket here, so it's going to be not P12 or B11 and not P21 or B11. This is based on the distributivity law of this O over this AND. And now if you notice, all our terms are disjunctions. So they are clauses, and therefore they are in a form that we can apply the resolution rule. Okay, so the original sentence is now in CNF as a conjunction of 3 clauses. It is much harder to read, but it can be used as an input to our resolution procedure. So we're going to try and apply the resolution procedure to solve this next. Okay, so we have seen how to convert a normal sentence into conjunctive normal form. Let us now try to see how to actually use this resolution algorithm to come up with the inference procedure. So here it says inference procedures based on resolution. They work by using the principle of proof by contradiction. That is, to show that KB entails alpha, what we do instead is we show that KB and not alpha is unsatisfiable. That is, to show that KB entails alpha, we only need to show that KB and not alpha is unsatisfiable. Okay, if it is unsatisfiable, then we have been able to prove that actually KB and alpha is satisfiable, and that is what is equivalent to this KB entails alpha, as we discussed earlier. So first, KB and not alpha is converted into CNF. Then the resolution rule is applied to the resulting clauses. Each pair that contains complementary literals is resolved to produce a new clause, which is added to the set if it is not already present. The process continues until one of 2 things happen. 1, there are no new clauses that can be added. In this case, what it means is KB actually does not entail alpha. Or 2 clauses resolve to yield an empty clause. Anytime you're able to obtain an empty clause, then you have reached the contradiction, and therefore you can conclude at that point that KB entails alpha. Okay, so that's what we are saying here, that empty clause is equivalent to false, because a disjunction is true only if at least one of its disjuncts is true. But the empty clause doesn't contain anything, so it doesn't have a disjunct that is true, and that is why it is equivalent to false. Now the following shows the resolution algorithm. Before we take an example to show how it works, let us state the algorithm complete. Okay, so PL resolution algorithm, PL for propositional logic. So it takes input, the KB and alpha, the knowledge base, and the query sentence alpha. It will also have as a variable the set of all clauses in CNF representation form, which is obtained by ANDing KB and not alpha. Okay, so these are clauses. It initializes a new set of clauses to be empty, and then it starts a loop. For each pair of clauses, CI and CJ, in the set of clauses, it will invoke PL resolve. So try to resolve CI and CJ and return a result. Now, if that result contains an empty clause, then we are done. Simply return true. Otherwise, update your new set of clauses to be the new plus the resolvent. So basically, this new set of clauses will keep increasing. If at any point the new set of clauses is a subset of the set of clauses, it means we will never be able to reach empty, and therefore we can stop and return false immediately. Otherwise, just update the new to the clauses and continue the process. So this is the resolution algorithm. We're going to show it more clearly with an example, of course using our Wumpus world. So the following figure shows an application of the resolution procedure to a very simple inference in the Wumpus world. Okay, this is the figure. When the agent is in 1-1, obviously there is no breeze, so there can be no pits in the neighboring squares, no pits in 1-2 and no pit in 2-1. So we can say that our knowledge base consists of R2 and R4, which is the same as there will be breeze in 1-1 if and only if there is a pit in 1-2 or a pit in 2-1. So this is R2 actually, and R4 is not B11, if you recall. Now we wish to prove that no pit in 1-2. There is no pit here. Okay, so when we convert KB and not alpha into CNF, we obtain the clauses that are shown at the top of the figure. If you recall what we did last time, these are exactly the figures that were, these were the clauses. These were the clauses that were obtained when we convert this KB and not alpha into CNF. So what we will be doing is we will be applying the resolution procedure to resolve any literals that are opposites. One of them is true, one of them is false. We resolve it by adding the resulting clause to the set. So for example here, if you look at this, how do we obtain it? We obtain it by resolving this clause and this one. Basically, if you check here, there is not P21 and there is P21, and therefore they will resolve and give you not B11 or not P12 or not B11. So this is the new clause that we're going to get. Okay, similarly, if instead of looking at not P21 and P21, suppose we look at B11 and not B11. So those can also resolve and give you a P12 or P21 or not P21. Okay. Similarly, this is obtained by considering this and this, where we resolve not P12 and P12. So we will be left with not B11 or P21 and B11 or B11. Okay. And similarly here, so far we have not obtained empty, so we keep going. This is obtained by resolving not B11 and the first cell here. So obviously the B11 and not B11 will resolve, and you are left with only not P21. Okay. And this one is obtained by looking at these two. They have B11 and not B11, so we have not P12. And this is a critical point now. See, we have not P12, but we have P12. So if you resolve them, they will give you an empty clause. And this empty clause is a contradiction. It means, therefore, that we have reached where we want. Okay, so it says here the second row shows the result of applying resolution to the various clauses after converting the expression KB and not alpha to CNF, and the last one produces the empty clause, which is a contradiction. So once we reach the contradiction, it means this and actually is not true, and therefore KB actually KB and alpha is satisfiable. In other words, KB entails alpha. So at that point we can prove that there is really no pit in 1, 2. This is basically how the resolution algorithm work. So that's the basically how to apply it. So in summary, before we conclude, we have learned in this lecture that knowledge-based agents are more powerful than problem-solving agents because of two things. One, in addition to perceiving percepts, they also maintain a knowledge base, which they can use to do the second part, which is they have inference procedures that allow them to infer new knowledge from the KB as well as the percepts. So this being able to infer new knowledge is what makes them more powerful. Actually, we should know that these knowledge-based agents are the building blocks of expert systems. Okay, expert systems are developed based on this idea. All right. What is knowledge base, as we have learned, is simply a set of sentences that describe the world and its behavior, and is represented in some formal language, usually a variant of logic. Okay. What is inference engine? It's a set of procedures that use the representation language to infer new facts from known facts, okay, or to answer a variety of queries relating to your knowledge base. Okay, and we have seen in this lecture a number of approaches to do so. The first one, which is not very efficient, is the model checking, where you have to check all possible models, and then we saw how you can do that by applying rules with the help of a searching algorithm. You can also do that. And then the last one is using the resolution. Okay, so the resolution actually is a very powerful method. There are ways to make it even more powerful, but we will not look at it in this lecture. Okay, Finally, we know that knowledge representation language is generally one or more variant of logic. Okay, and propositional logic is the simplest of such logic. Another more powerful type of logic, which we will not be able to study in this course, is called first order logic, FOL. There are also higher order logics that are even more expressive than FOL. Okay. The key aspect of knowledge representation that you should all remember is that it involves syntax. Syntax basically describes how sentences are formed in the language. It involves semantics, describing the meaning of sentences. That is, what is it the sentence refers to in the real world. Okay. And finally, it involves some computational aspects that allow you to describe how sentences and objects are manipulated. Okay, so this is the basically a brief about knowledge representation and how they are used to infer new knowledge from existing knowledge. We will stop here. Thank you very much.